Hey guys, welcome back. This is Mr. Kim. I'm going to go over this time the 2023 August Chemistry Regents, the FRQ section. So let's get started. Number 51. The four naturally occurring isotopes of sulfur are sulfur 32, 33, 34, and 36. State the number of valence electrons in an atom of sulfur 32 in the ground state. All right, so this one, like, once again, has nothing to do with this problem of these three things. It really is just asking you if you understand the definition of an atom, right? So it says state the number of valence electrons in a sulfur. That's all it's asking, right? So if you go to sulfur, what do we notice? The number of valence electrons is the last set of electrons right here, right? So therefore, the number would be actually 6, right? See that? So your answer here would be 6, like so. Okay, let's go to 52. State the number of neutrons in an atom of sulfur 33. So you got to figure out that 33 is what? The number of protons plus neutrons. And how many protons does sulfur have? You go to sulfur again, and you notice sulfur has atomic number of 16, so therefore it has 16 protons, right? So what does that mean? That means that 16 plus neutrons is equal to 33, right? So what's the difference? That's 17, right? So 33 minus 16, right, equals 17. And that would be our answer. Okay, number 53. So 53, 55 is a set. Group 1 elements below hydrogen are called alkali metals, and the first 5 group 17 elements are called halogens. Compare the electrical conductivity of an alkali metal at STP with the electrical conductivity of halogen. Well, first of all, this one, you don't need to go anywhere. What do we know? They want to know if you know the definition of metal versus non-metal, right? So therefore, you would say alkali metal has a higher conductivity than that of halogens. Okay, that's all you need to write. 54. State the type of chemical bonds formed when an alkali metal and a halogen react to form a compound. Now, you might remember by definition what metals and nonmetals form, but if you don't remember, then you can always pick a representative metal and a representative nonmetal and put it together, and then you get NaCl, which is what? Ionic, right? And if you didn't know that sodium chloride is ionic, I don't know, man. I can't help you with that, right? So the answer would be ionic. Okay. Okay, let's go to 55. Explain in terms of electrons why the halogens are all placed in the same group. Remember, that's going up and down in the periodic table, right? In terms of electrons. Well, what do we know? Again, this is not asking about halogens. It's just asking you if you understand what the trend is in a same group. So we know that in a same group, what do we know? Well, in the same group, the number of valence electrons is the same, right? So, you would write here that go back for a second, halogens are placed in the same group, right? Halogens all have 7 valence electrons, and elements are grouped according to the numbers of their valence electrons, right? All right, let's continue to 56. I'm guessing already that for 56, they just want you to balance this thing, but let's just go double check. 56. Balance the equation in your answer booklet for each reaction using the smallest whole number coefficients. Let's go. So looking at this, what do we understand? We got two aluminums on the right side and we have blank on the left side. But remember, stuff like aluminum here and silver here, I'm going to save that till the end, right? Because I'm going to work with somebody else first. So going over here, let's look at and balance the sulfur first, right? So we got 3 sulfurs on this side. So we're going to have to balance that by putting 3 on the other side. By doing that, then the silver on the left side becomes 2 times 3, which is 6. So we're going to need 6 silvers on this side, right? And then because of the 2 aluminum on the right side, you're going to need 2 aluminums on that side. So your number should be 3 to 6. Now, it looks funny because it looks like they could be simplified, but you do realize you can't simplify this, right? It's not possible. So this is the lowest set of coefficients. But always double check that you don't accidentally put like 6, 4, and 12, in which case you would have to simplify, right? But not necessary here. 57. Determine the gram formula mass of aluminum sulfide product, right? It's a product right here. They want the gram formula mass. Well, it's Al2S3, right? So they want the Al2S3. So that means it's 2 times the molar mass of aluminum, which is right here, 2698, 26.98 plus 3. Sulfur is 32 and a change, right? 32.1. Right? And they don't want the work, they want the actual answer, right? So in this case, what do you end up with? I don't have the number, so I need to calculate this. So give me 2 seconds for me to punch this in. 2698 times 2 plus 3 times 32.01, right? It's all 1, I believe. Nope, 32.1, right? And I get 150.26. All right, so I'm going to say 150, right, grams per mole. Okay, let's continue. 58. Show numerical setup. So again, be careful, right? They want the setup. They don't want the answer, so don't go punching this into a calculator, right? Calculating the number of moles of silver sulfide in a 546 gram sample of silver sulfide. So this is our start. And this is what we want as the answer, right? So, and then they even gave us a gram formula mass. So this can't get any simpler, right? So we start with our 546. We start with our 546 grams of our Ag2S. And then put a fraction bar. You want, in the end, we want moles of silver sulfide, right? Moles of silver sulfide. So what do we know? We know we want to get rid of it down here, right? And then you want moles of silver sulfide, which means that in terms of units, this will cancel that. So we're good to go. So the question is, do we have this value? And the answer is yes, we do, right? They gave it to us right here, right? 248 grams per mole, right? Now, if they didn't give it to you, you can go look it up, right? You can go look it up because it's, what is that? It's 2 times silver plus sulfur should give us the same 248 as the value, right? And therefore, this is actually the setup. And look what happened. Mr. Kim also, he tried to answer the question, right? Remember, they don't want you to answer the question. They want you to give you the setup. So that's important. Okay, let's move onward. Hydrogen gas and iodine gas can combine in a reversible reaction to form hydrogen iodide gas. The equation below represents a system in equilibrium in a sealed rigid container. Now, a couple of things before we move on. What do I immediately notice? I immediately notice energy on the reactant side. Energy in the reactant side means energy is a reactant, so therefore it's going into the reaction, right? So that makes this endothermic, right? Now we might not need it, but I'm just noticing that. State the evidence from the equation that the forward reaction is endothermic. Bro, I literally just answered this, didn't I? Right? So endothermic means what? Energy is going into the reaction, and in here, what do we notice? Energy is on the reactant side, right? So you would say energy is on the reactant side, right? And that should really be it. That's you don't really say more about that. State in terms of reaction rates why the concentration of hydrogen iodide remains constant when the system's at equilibrium. Once again, right? They've last what 4 FRQs I looked at, and it's the same exact question. At equilibrium, both forward rate is the same as the reverse rate. Okay, so you would say here, literally, the rates are the same. You might even want to say at equilibrium. Okay, let's go to 61. State how an increase in temperature affects the concentration of HI. So what is HI? HI is right here, right? So that's products, okay? And increase in temperature, what do we know? Increase in temperature means that you're raising heat energy, right? Which is what? Raising energy is what? Reactance, right? Which means more products. All right. So write that increasing temperature means increasing heat energy. Hello. Oh, computer's freaking out. Come on, let's write. Okay. This reaction is what? Endothermic, right? So increasing heat will make the reaction go to the product side. So HI will increase, right? Now, this is really important. In fact, I should have started my answer with that because, right, they wanted to know the effects, right? So I should have started with the effects and I should have started my answer with the HI will increase, but that's okay. I said it in the end. All right, let's go to 62. 62 Okay. All right. Equation below represents a reaction of straight chain butane with chlorine. So this is organic, right? Now, be careful. Remember, even if it's organic, not all the questions are organic questions. So don't start freaking out. The reaction produces two different isomers of C4H9Cl. What are isomers? Isomers are things that look exactly the same in terms of formula, but the location of the atoms in the structure is a little bit different, right? 1-chlorobutane and 2-chlorobutane. The table below shows the boiling point of each isomer at standard pressure. Number 62, state in terms of carbon-to-carbon bonds why butane is saturated, right? Now, if you're in my period 1 class, we covered this already, right? Definition of saturated is what? It means that it's all carbon-to-carbon single bonds, right? So, state in terms of carbon-carbon bonds why butane is saturated. So, saturated hydrocarbons have all carbon-to-carbon single bonds. Okay, that's it. Because remember, because they're all single bonds, then therefore they have all these maximum number of bonds, sticking out of the carbon. So therefore you could have as many hydrogen as possible coming in and saturating the molecule, right? That's what's called saturated. Number 63, identify the class of organic compounds to which organic product in the equation belongs. So let's go. Organic product in the equation. Who is it? Well, that would be this guy, right? Right? That's the organic product because HCl is inorganic, right? Because we covered that when we were doing the inorganic portion of this course and in form of acid. So let's go take a look. So what do? We go here to the chart of our identification. If you go here, what we're going to do is we're going to look for something that looks very similar to what C4H9Cl is. C4H9Cl is, right? So now let's take a look. What gives this away? It's the halogen, right? So is there something that has halogen? Going around, and what happens? Oh, look at that. We do have one with a halogen, right? And it says X represents any halogen that's attached to this. So therefore, C4H9Cl looks a whole lot like this. In fact, it's the only one that has halogen in this entire chart. That makes this a halocarbon or halide. So your answer for this would be halide, or you could also write halocarbon. Either answer is acceptable and correct. All right, let's go to 64. Based on the boiling point data, what does that mean? Boiling point data, it's up here, right? Compare the strength of intermolecular forces in 1-chlorobutane to the strength of intermolecular forces in 2-chlorobutane. Now, let's just summarize this for the last time, right? Stronger intermolecular force means what? Molecules are stuck tighter, right, to each other, right? Which means what? Difficult to boil off, therefore higher boiling temperature. Okay, that's what this means. So what does that mean? That means if you look at this, who's got a higher temperature? That's this guy. So therefore, we would assume that this IMF is stronger, right, than that of 2-chlorobutane. And that's it. That's literally what you write. So you would go here, right? 1 chloro is it tane or teen? Tane has stronger intermolecular forces than 2-chlorobutane. butane. Done. Let's go to 65. Draw a structural formula for the 2-chlorobutane. All right, so let's try to figure this out, right? Let's break this down. It's butane, right? But is what? Let's go. And then you should know this. But but means 4 carbons. So let's go put that down. 1, 2, 3, 4. Now, let's see. It's an ane, right? Ane means all single bonds, right? So we're already correct. Now, what happens? It's 2-chloro. Chloro means Cl, right? Where does that go? It goes to spot number 2. So if we number this 1, 2, 3, 4, that means the chlorine is going to go to carbon number 2, right? You could also number this backwards, right? 1, 2, 3, 4, and in which case the chlorine will stick here. So that's literally what you're going to do. You're going to draw a butane, 1, 2, 3, 4, and make it big enough, guys, right? So it's easily visible. And then on the second carbon from either side, you're going to stick in a chlorine. And then what happens? They're all single bonds, which means that each carbon needs to make up to 4 bonds. So you're going to make 3 more here. This already has 2, so 2 more. This carbon has already 3, so you make 1 more. And then the one on the leftmost, it's already got 1 bond, so you're going to make 3 more bonds. And what happens? Each one will be filled, remember, with hydrogen, like that. Now, do you have to fill in the hydrogen? The answer is no, but that's fine, okay? Let's keep going. 66. Number 66. Let's take a look. All right, so this is a biggie. It's 66 to 85. It's a lot of questions, okay? During laboratory activity, appropriate safety equipment was used and safety procedures were followed as 2 students worked with hydrated copper 2 sulfate. A hydrate is a compound that has a water within its crystal structure. So when you're taking this on your own, did you, when you get to CuSO4, just say CuSO4, or did you actually take the time to try to name it? Because that's how you get extra practice, right, guys? So this is copper 2 sulfate, right? I mean, where else are you going to practice this? Student 1 and student 2 each heated their own 3-gram sample of hydrated copper 2 sulfate. Student 2 determined the percent composition by mass of water in the hydrated copper 2 sulfate to be 37%. The accepted value is 36.1. So I'm smelling that they're probably going to make us do percent error somewhere. The final mass values for each student sample are shown in the table below. Number 66, state the number of significant figures in the mass of the hydrated copper 2 sulfate sample used by student 1. Now, what does that mean? Well, first of all, are they joking? Because all the numbers in this chart have a significant value of 3, right? But specifically, they're looking at mass of the hydrated copper 2 sulfate. So that's this one by student 1. So 3.00 has how many sig figs? 3 sig figs. Okay, let's go to 67. Determine the percent composition by mass of water in the hydrated sample based on student 1. So we're only looking at student 1 right now, right? So let me erase this and let's take a look. We're looking at mass of water in the hydrated copper 2 sulfate solution. So if you think about that, then what do we need to do? Well, we have this. This means with water. This is after heating. This is without water. So how do you think we figure out the mass of water? What do you think? It's the difference, right? So we know that the mass of water is probably going to be 3.00 minus 1.98, right? That's going to be the mass of water, right? So then with the percent composition. So what is percent composition? If you don't know, it's going to be the amount that you're looking for over the whole, right? Or if you're not sure, think about it. It's always here, right? Percent composition by mass is right here. It's mass of the part over mass of the whole, right? And what is the part? Part is this part was water. And then this is the whole, which is everything, right? So let's go. That's going to be what? Water is going to be, it's going to be 3 minus 1.98. And if you put that into the calculator, you should get 1.02 grams, right? Is what you get. That's the part over the whole thing is what? Whole thing is the thing with water, right? Which is mass of the hydrated copper sulfate, right? So that would make it 3.00. And remember, it's times 100, right? And that should come out to a value of, I think, 34.0, right? All right, so let's continue. 68. Show numerical setup. So notice I'm circling it, right? Please make sure you circle it when you see that, so then you write the setup, not the actual answer. For calculating the percent error or the percent composition by mass, percent error. So let's go. Percent error is right up here. Is the measured value minus accepted value over accepted value. So if you take a look, right, they said student number 2. So now we're going to go over to student number 2. Percent error for the percent composition by mass of water and hydrated copper sulfate. All right, so you have to be careful. They gave it to you right here, right? Look at this, right? This is student 2, all the way up here. So you can try to recalculate the numbers and waste your time, but they already gave it to you here, right? Where this is, right, the what is it called? This is the measured. The student 2 measured this, but the accepted value is this. They literally gave it to you. All right. So therefore, how do you do this? It's 37 divided by 36.1, right? So it's, I forgot the number. It's going to be what again? 37.0, right? Minus 36.1, right? Now, over what? Over the accepted value, right? So it's going to be over 36.1. Don't forget the 100, right? Because if you forget that, it'll be wrong, right? And please circle your answer. And there it is, right? 69. Ammonia is a compound that is used to manufacture fertilizer for agriculture. Hey, I talked about that, right? The Haber process. This gas is produced by reaction between nitrogen and hydrogen. During the reaction, bonds are both broken and formed. Bond energy is the amount of energy required to break 1 mole of bonds between atoms in the gas phase. The bond energy of an HH bond is 436 kilojoules per mole. All right. State the number of electrons shared between nitrogen and one of the hydrogen atoms in ammonia molecule, right? Now, you can go crazy and draw it out, but if you think about it, dude, what are we talking about? Hydrogen and nitrogen. We're talking about a bond, right? How many electrons make up a bond, right? I asked period 1, and then every time I ask, Abel seems to be the only person who raises his hand, and then he makes a V, right? It's 2 electrons equals a bond, right? So it's 2. The answer is 2, right? So it's 2. But if you don't know, you can waste the time and draw the loose diagram. 1, 2, 3, 4, 5. And then you have hydrogens like this, right? And you have the hydrogen electrons. And if you can tell, there's 2 electrons being shared, right? But it's a bond, right? They're asking you how many electrons are in a bond. That's literally what 69 is asking you. Number 70, identify the noble gas that is atoms in the ground state with the same electron configuration as a nitrogen atom, the molecule of ammonia, right? Let's take a look. Ammonia is NH3. What do we know, right? You guys remember, we got to figure out the charges, right? So how do you figure out the charges? There's no rule for nitrogen, but there's rule for hydrogen, right? What's the rule? What do you think? Right? So rule for hydrogen is it's +1 if it's paired with a non-metal, and it's -1. Did I screw that up? No, it's +1 if it's paired with a metal, No. I messed that up. Sorry. It's +1 when it's paired with a non-metal, and it's a -1 if it's paired with a metal, right? Now, if you notice, you're thinking, gasp, why doesn't Mr. Kim remember that rule? It's because I don't really care about that rule. Because remember what I said? Hydrogen and nitrogen. Look at the nucleus. Who's got a smaller, weaker nucleus? That's hydrogen, right? Why? It only has one proton, right? So therefore, who's having an easy time holding onto the electrons? Nitrogen is, because it's got a stronger nucleus. So, which means that hydrogen is going to lose its electron to the nitrogen. Everybody okay? And also, nitrogen is more electronegative, right? Anyway, so that means that H is going to be positive. So that means that N is going to have an oxidation number of -3. How did we get there? This means nitrogen gained how many electrons? 3 electrons. All right, so let's take a look. If you go to the reference table, right, and you go to nitrogen, if nitrogen has 2-5, and if it gains 3 more electrons, what are you going to end up with? Gaining 3 electrons will give you 2-8, right? Who's that? That's neon, right? And neon is the noble gas, isn't it? So the answer is neon and E, 71. Determine the energy required to break all of the bonds and 0.25 moles of HH bonds in the H2. Again, right? Everything's been given to us. This is our start. Determine the energy required. This is our end. And we need some sort of a ratio because it's dimensional analysis. And ready? Look at that. It's right here. Do you see that? Energy per mole. So that's all we have to do. Let's go set it up, right? So we start with our start, which is 0.250 moles, right? Of who is this? HH bonds, right? Right. Now, you want to get rid of the moles and end up with kilojoules, right? That should give us kilojoules, right? Because what do we know? Moles is going to cancel out moles, right? But do we have this value? The answer is sure we do, right? It's right here, 436. So it's 436 kilojoules per 1 mole. And let's do the math, kids, right? So what do you end up with? 436. You're taking a quarter of that, right? So it should be 109, right? You punch that into a calculator, right? But it's actually easy, right? Because 4 times 9 is 36, and 4 times 1 is 4 times 100 is 400, right? All right, so there it is. Let's go to 72. All right, so this is what? Gas laws, right? Why? I see PV and a T, right? I already know that, right? P1 V1 over T1 equals P2 V2 over T2. That's already coming into my head. The diagram below represents a sealed rigid cylinder with a movable piston containing helium gas at 296 kelvins, that's a temperature, and 1.3 atm, that's pressure. Oh, they gave it to us right here, down here. Compare the density of the helium in a cylinder when volume is 50 to the density of the helium in the cylinder when the volume is decreased. All right, so let's take a look. You guys remember from class what density is equal to? Remember, density is equal to what? What is it, kids? Waiting. Broken heart, right? Density is equal to a broken heart. So what does that mean? What's on the top of the heart? Mass. What's on the bottom? Volume, right? So that's how I remember our density, right? Although I think it's in here. So unnecessary, but I'm pretty sure it might be in here. Maybe not. Let's just take a quick look. Yep, they actually give it to you, right? Look at that. But you don't need it, right? You don't need it. If you need it, it's here, but you remember density is equal to broken heart mass over volume, right? So going back here, right? So what do we know? Well, look, volume equals 50 versus volume equals 25. What are we doing here? You're going to take the same mass, right? Mass is the same. Did they tell us a mass? They didn't, but you know the mass is the same. We're not changing the mass. So essentially in this case, right, density is going to be mass divided by 50 whereas over here, density is going to be the same mass divided by 25, right? So who's going to have a smaller density, right? The one where it's 50 because you're dividing by a bigger number, so it's going to be a smaller answer, right? And who's this? This is a volume at 50, right? So you say the density when volume is 50 milliliters will be smaller than the density when volume is 25 milliliters, right? That's all it is. They're just asking you if you understand the algebraic relationship between the mass and the volume. This is not really chemistry, it's algebra. Go to 73. State one change in temperature and one change in pressure that will cause gas in the cylinder to behave more like an ideal gas. All right, so this is definition. Remember ideal gas? Ideal gases do not interact with each other. So how do you make real gases do that? We need to separate them. All right, how do you do that with temperature? How do you make gas molecules move further away and not cuddle up, right? So you make it what? Move further out, which means how do you do that? You heat it up, right? Higher temperature, molecules are further apart. Cold temperature, they huddle together, right? So you want high temperatures. What about pressure, right? At high pressure, what are you doing? You're squeezing them together so they're going to be closer, and you don't want that. You want to separate them. So what do you want? You want low pressure, right? So ready? Temperature. What do we say we want? We want higher. And then what do we want for pressure? We want lower. Okay. All right, let's go to 74. Um, sorry guys, I just got distracted. I saw a text message. Mrs. Kim said, I might be a genius. Let's see. Oh, yes, she's a genius. How? None of your business. All right, let's go. Question 74 and 76. Four different samples of sodium nitrate. Again, did you name this when you saw this, or did you say NaNO3? Because anybody can say NaNO3. So when you see a chemical formula, try to name them, right? That's a really good way to practice naming to get ready for the regions. The solution volume and the mass of dry sodium nitrate of each sample are recorded in the table below. And by the way, if you're like, how do you know how to name that? You remember NO3? What's that? Polyatomic ion, table what? Not telling you, got to figure that out. All right, so let's go. The number of moles of sodium nitrate of each sample was then calculated and used in the graph below. Okay. Determine the number of moles of sodium nitrate in 0.15 liters of the solution. All right. Well, what are they're asking you, do you know how to read a graph? Dude, if you get this one wrong, you're literally telling the grader, I don't know how to read, right? Number of moles of sodium nitrate is right here, isn't it? Liters of solution is right here. So let's go. 0.15. 0.15 is right here, isn't it? Go up. It's right here. Moving across. Oh, what happened? Moving across, what do we get? What do you think? Right? That is halfway point right here, right? So that's, what is that? That's half between 0.15 and 0.10. That's approximately 0.125, right? It's just smidge under. So I'm going to assume that that's 0.12. Close enough, right? So I'm going to say it's 0.12. Okay, everybody okay? All right. I did look at the key just now, and it says the range is 0.11 through 0.13. So any answer between these two numbers is acceptable. So 0.12, literally smack in the middle. So that's a good answer. Let's go to 75. Write the chemical name for sodium nitrate. Do you realize this, right? Do I know how to tell or do I know how to tell, right? What is this? This is sodium. What's that, right? Again, I'm going to show you now how to do it in case you didn't know, right? Where do you go? That's polyatomic ion, right? So you go here. Nitrate, right? So it's nitrate. But if you've been doing what I've been asking you, you should have figured this out already, right? So that would be sodium nitrate. Now remember, if you did not practice naming things as you see these things, what's going to happen is you're not going to be able to do this. You're going to be like, is that sodium nitrogen trioxide, right? Right. Some of the things I've heard, written by some of the students before, some kids will write really stupid things like sodium, nitrogen, oxygen, or oxide. They'll write sometimes monosodium, mononitrogen trioxide. That's also wrong, right? So, like I said, please practice. When you see a chemical formula, try to name them, right? And that's a good way to practice. Compare the boiling point of solution in sample 1 at standard pressure to the boiling point of water at standard pressure, right? So you're thinking, well, what are we talking about? What are we talking about? Hey, guys, it's a solution. They're saying compare the boiling point of a solution versus boiling point of water, right? So what do we know? Salt water versus pure water, right? What do we know about salt water? When does it boil? Does it boil at a higher temperature or low temperature or at the same temperature, right? And this, I can't help you. This is something that we did in class, and it's definition of colligative properties. So you should know this, right? So we know that salt water, right, has a higher boiling point than the water. Okay. So you would say solution has a higher boiling point than pure water. Okay. Number 77. Oh, look at this, right? Electrochem, right? What do you write? That's my jam, right? Because why? We're good at it because remember, we had the highest class average. All right. However, oh, take a look. All the other FRQs that we've seen so far, because we started at the latest one and we've been moving backwards, have been voltaic. What do we notice, guys, up in this one? What are we looking at? Hmm? That's right. We're looking at electrolytic, right? How do we know this? Power source gives it away. And what else? One beaker, right? You remember? I said if you have one beaker, electrolytic could be in one beaker. Voltaic has to be in two beakers with a salt bridge, right? So we're looking at electrolytic. So a couple of things change in this one, don't they? Right? So let's think about this. Okay, so a copper rod and a bracelet made from different metal. The rod and bracelet are in an aqueous copper 2 sulfate solution. Okay, here we go. Identify the electrode that attracts the Cu2 plus ions as the cell operates. Okay, so think about it. Cu2 plus ions go to where, right? You remember opposites attract, right? Which means it's going to go towards the electrode that is negative. You remember in voltaic, I'm sorry, electrolytic, What did I say? The sign of the electrode is the extension of the power source. So see this plus? That gets all the way extended out to here. See that negative? That gets extended out to here, which means the copper 2 plus ions are going to go to where? To negative or positive? It's going to go to this one, right? So what is it going to? What do you call that? Well, just use the word they gave in the diagram. It's bracelet, right? So you're right, bracelet. But if you want it to be more scientific, what can you use? Well, you can also say that what? Or you can say negative electrode. That's an acceptable answer. What else can we say? Well, you can say anode cathode. I would advise against that because you might get a little brain fart and then say it in the wrong way. Normally what? Cathode is positive, but only in what? Voltaic, right? Remember what happens? In electrolytic, cathode is now negative, right? So the negative bracelet would actually be called cathode. So you could also write cathode, but like I said, I would not try to use the word cathode because of that, because it flops, flip flops, right? Let's go to 78. Determine the oxidation state of sulfur and copper sulfate. All right, so let's solve it two different ways. You can try to solve it the long way, like this, right? In which case, who do you tackle first, right? Let's tackle the oxygen. Oxygen is minus, let's use different colors, right? So it's easier for you to identify, right? CuSO4, right? And then what do we know? Well, oxygen is -2, but there's 4 of them. Therefore, oxygen is -8 total, right? And then you got to look at copper and you're like, well, what's going on with copper? See, this is where it gets all iffy because you don't know if it's copper 1 or copper 2. That's why I said it's really important if you know how to read these. See, I said it's copper 2 sulfate. How do I know that? Because what gives it away? It's the sulfate. Remember, it's polyatomic ion. If you go to sulfate, what's sulfate? Sulfate, where are you? Sulfate is right here, right? It's -2, right? So therefore, you know that the copper is not +1, but it's supposed to be +2 because it's neutralizing the -2 in a sulfate, right? So what does that tell you? That tells you a total of -8 for 4 oxygens, +2. So therefore, this has got to be +6, right? So that's our answer. See, the other way to solve it is also like this. You could also solve this by just doing SO4 2 minus, right? Because you know that the sulfate is actually part of the copper 2 sulfate. So if you do it that way, it gets a little bit more simpler because you know the oxygen is -2, right? Except we have 4 of them. So total is -8. And what happens? The sulfur neutralized all of the 8 except for the 2. So therefore, it's got to be +6. That's another way to figure this out. Okay. So it's +6. Everybody good? All right, let's keep going. Write the balanced half reaction equation for the reduction of copper 2 plus ions that occurs in the cell. Well, look, at this point, right, hopefully you've been knocking out enough of these FRQs to understand reduction of copper 2 plus means what? It means ions going into the bar or the solid, right? So that means what? Copper 2 plus going into the copper bar, right? You remember in reduction means the bar is growing, it's getting larger. And how do you charge balance this? Right? You need 2 electrons on this side, right? Don't forget this. I've seen some wacky stuff that kids write. They'll do stuff like this and then put the electron on the wrong side. Remember, electron is added to make the charges on either side equal to each other, in which case, in this case, it's 0. So let's go and fill that out, right? So what happened? Reduction, hello. Reduction, right? reduction of copper 2 plus aqueous, right? Now, the other way to think about it is reduction is what? Leo the line says GER, right? Reduction means gaining. So you know the electron must be gained as a reactant, right? So the answer is 2 electrons. Now, one of the things that I noticed and looking at the keys on all of these, right? One of the most important thing is, dude, do not forget the negative symbol on the E. If you leave the negative symbol out, it's wrong. The keys on these exams explicitly say to the grader, if the student didn't put a negative symbol on the E, mark the whole thing wrong. So don't forget that negative symbol. You guys remember in class, especially period 1, I'm talking to you guys, right? I'm looking at you. You guys keep dropping charges when you feel like it. Do not do that because you're going to get it wrong. I say this every year to students. Do not drop charges. You're going to get stuff wrong. And what happens? Couple of kids in that class every year will leave out charges, even though Mr. Kim told them over and over throughout the year, stop forgetting charges, and then they'll do it, right? So doesn't matter. I don't care if you have a tutor who doesn't seem to care. And then where if you say, CL instead of CL minus, the tutor's like, oh, that's okay. It's not okay. Okay. That's why they're a tutor. I'm a teacher. So do me a favor. Please do not forget the charges when you mean charges. Okay. All right, rant over. Let's go. Let's look at number 80. Like, look at this, right? I already know what this is. Why? How do you know? Guys, take a look. What's HCl, right? Remember I told you you should really recognize them, memorize the chart. That's table K. That's acid. What's KOH? That's an Arrhenius what? That's an Arrhenius base, right? If you don't know how to identify it, man, you should be going studying in how to figure out Arrhenius bases, right? All right. So here we go. So let's go to the question. It says, complete the equation in your answer booklet, right? Well, let's go read it first, right? And it's titration, right? Again, immediately as you see titration, what am I thinking, right? I'm seeing this, right? 15 milliliters of hydrochloric acid, that's volume, right? Of unknown concentration. Hey, it says we don't know the concentration, right? Is exactly neutralized by the addition of, what's that? That's volume of our base, KOH, and that's what? Molarity of base. How much you want to bet that they're going to make us calculate the titration, right? The pH value is 1.1 before the titration begins, all right? Let's go. Complete the equation in your answer booklet for the reaction that occurs in this titration by writing the formula each product. All right, let's go. Well, look, guys, it's acid plus base gives you what? Salt and water, right? So, water is a product. And what do we say? Neutralization or titration is a subset of what kind of chemical reaction? What is it? Double replacement, right? So since the H and the OH fell apart and made water, what are we left with? We're left with K and a Cl, right? Now, but before writing it, double check. K is what? Group 1 plus 1. Cl is halide minus 1. Crisscross drop charges, it's KCl. Be careful. You gotta write your formulas correctly, right? In this case, it's just KCl. Let's go to 81. State the pH value of the solution when the H plus ion concentration in the acid has decreased by a factor of 10 compared to its original value, right? Now, I kind of set this, on the fly. I didn't have it literally in the PowerPoint. So I don't know. I don't know how many of you actually wrote it down, but log of 10, sorry, I wrote it wrong. Log of, you remember what I said? Log of 10 is what? 1, right? Because it's how many tens raised to its exponent, right? Log of 100 is what? 2. If you don't believe me, put it in your calculator, right? So what does this tell you, right? Log of 1,000 would be 3, right? So let's look at this. From here to here, 10 times what gives you 10? 10 times 10. And what happened? It went up 1 place. From here to here, 100 times what gives you 1,000? times 10 again. And when you go 10 times, what happens? Log goes up by 1. So what does this tell you? That tells you that whenever the pH changes by a factor of 1, the concentration that you're taking the log of is 10 times higher or lower, depending on which direction the pH is moving. All right, so let's take a look and see if you can answer this. State the pH value of the solution when the H plus ion acid is decreased, which means what? pH is going to go in which direction? pH is going to be more acidic or basic if the H plus is decreased. Think about that, right? Think about it. Don't just blurt out because you know you're going to say it wrong, right? Think about it. Decreased. So if you're decreasing H plus, and what's H plus? It's an acid, right? It doesn't matter whose definition you use, right? So therefore, since you're decreasing the acid, it's going to be more basic, right? Or pH is going to go up, right? Up from what? Up from 1.1, okay? From 1.1. Now, how much though? Factor of 10, which means what? It's going to be, the log is going to change by 10 times, which means your pH is going to go up 1 whole unit, right? Which means it's going to go up from 1.1 to 2.1. Okay, that's it. All right, so the answer is 2.1. All right, let's go to 82. Determine the molarity of the HCl by using the titration data. Here it is, right? That's literally what they were asking us to do. So let's go. We got Ma, Va, Mb, Vb, and like a good student, I'm going to set it up, right? So you want the molarity, that's our unknown, right? And let's go up here. We have all the value, 15.0 milliliters. Mb is 0.15 molar. And then below, Vb is 8 milliliters or 8.0 milliliters, okay? So let's set this up. You know that MAVA equals MBVB, right? Do you see what I'm doing right now? I wrote the base side first. And then you know on the left side is MAVA, but you know that you want the MA, right? Because we're looking for that. So you know this VA that I'm about to write here? I don't want that here. I want it somewhere else, right? Where do I want it? I want it down here, right? So what am I doing? I'm actually skipping a step, right? Which is literally what I tell you not to do, right? So now set this up. MB is 8.0 milliliters. VB, oh, I screwed that up, right? I mean, it doesn't matter, right? Doesn't matter what order you put this in because it's multiplication, but it's 0.15 molar times 8.0 milliliters all over 15 milliliters. Check that out. I don't even need a calculator for this, right? If you are uncertain, you can use a calculator, but dude, you know what I know about this? All I know is that 15 goes into 15, right? 15 divided by 15 is 1, right? 0.15 divided by 15 is 0.01. I know that. I know that much. I'm not an idiot. At least I don't think so. All right, so what does that mean? That means it's 0.01 times 8.0 milliliters, which is 0.08, okay? And it's 2 sig figs, right? 0.08, right? Molar is the answer. Again, you don't have to worry about it. You could just punch it all into a calculator and you'll still get 0.08. Let's go to 83. We're almost done. So that's done, right? Let's go. Oh, it's nuclear. And remember, so far, nuclear is pretty easy, right? I mean, we didn't even cover this unit yet. Yet, hopefully by now, if you've watched the video, which is like, only half of you, right? I don't know why. You should understand how to do this, right? Let's go. Nuclear fission is currently used to produce electricity in a nuclear power plant. One possible fission reaction is represented in the equation below. Barium-141 decays by beta emission and has a half-life of 18.3 minutes. So this might be important, might not be important. But you know, if they gave you the half-life here, it may not be on that table N, right? So be careful. If you go to table N, you don't see it and they ask for it, don't freak out. Let's go to 83. Based on table N, speaking of, state the decay mode for uranium-235. You should not get this wrong. Why? Because they're literally asking you to go read a chart. So let's go read this chart. Table N. Let's go to table N, which is right here. Table N. They want the decayed mode of uranium-235. Let's keep scrolling, keep scrolling, keep on scrolling, keep on scrolling, keep on scrolling. Uranium-235 is right here, right? What is it? It's this thing that looks like fish, right? What is that? That's an alpha particle, right? I think somewhere they tell you, right? I'm pretty sure they tell you. It's in the front. Right? Nope. They tell you somewhere. It's somewhere. I know it's somewhere, right? You should know it, but maybe not. Right? But whatever. It's right. It's alpha, beta, and gamma, right? So go to table N, go back to table N. Remember, look, take a look, right? Decay mode here, uranium here, they intersect right here. So it's alpha. So what do? Well, you can write alpha, or you can make the symbol, right? It either or. Okay. Look at 84. I know what they're gonna ask for 84, even before I get started. Do you? Right? All right. So it says complete the nuclear equation in your answer booklet for decay, right? This is the easiest thing. It's a little different this time, though. Let's figure this out. Remember what I said, right? On either side of the equation, the numbers at the top and bottom must be the same. So on the left side, what do we got? We got 141. On the right side is 0. 0 plus what gives us 141? That's what you need to ask. Don't sit back and just look at it and try to come up with a number, because 5 out of 10, you're gonna screw this up and then put on a wrong number. Okay, trust me on this, because kids do this. I'll show you examples of kids screwing this up, but you got to ask yourself, 0 plus what gives us 141? 0 plus 141 gives us 141, right? This is where I say it's really important, because this one is what? -1, right? So it's -1 plus this number gives us 56. What plus -1 gives you 56, right? Did you say 55? Because that's what some of the kids will do, and that's wrong. It's what? 57 minus 1 gives you 56, doesn't it, right? So how much you want to bet that kids screw that up, right? How do I know? Because I see it, right? All right, so now what do we do, right? I don't have to explain this, right? Hopefully you're watching this after you've done the other videos, at which point this is what? The fourth time I'm telling you how to figure this out, right? So what do? Look for atomic number 57. Where is 57? 57 is right here. Hello. So that makes it LA, not the city, like that. Okay? We good? All right, so let's go. 85, last question. We're feeling good. Compare the amount of energy released by the fission of one fission. What is fission, guys? Suckers what? Nuclear. Okay? To amount of energy released from combustion of fuel. Combustion is what? Chemical. Hey, what is more powerful, nuclear bomb or a chemical bomb, kids? Right? I mean, do I have to explain that? This seems so easy, right? But guess what? Every year, kid messes this up and say that the chemical has more energy. I don't know where that comes from, okay? I mean, what kind of bomb is the most powerful bomb? Nuclear bomb. So nuclear releases more energy than chemical. And that's literally what you need to write, right? Nuclear releases more energy. I'm not even going to write the other part with then chemical. You can, but I'm not even going to do that. And that brings us to the end of yet another FRQ. I hope this was helpful. Thanks for watching.